Okay, here we're in chapter 5 and the labs on cross-validation and the bootstrap. Validating models is really important, where you fit models on separate training data and then you evaluate it on test data or validation data sets that weren't involved in the training. And Jonathan's going to show us how we do it in this lab.
Okay. Thanks, Trevor. Yes, so one of the nice, we're going to be using scikit-learn sort of cross-validation setup, which is one of the nice things about scikit-learn is for all of its different models, you can cross-validate them in using almost the same code. We just have to swap out what the particular estimator is. So we'll in this lab we'll look at cross-validating least squares regression. So we're going to compare that with the train test split that we saw in chapter 4 for classification as well. So those will be the two things we'll look at. Okay, so there are a few new imports. So key imports to look at are this k-fold import. That's going to be how we implement k-fold cross-validation. The cross-validate function is what actually will be used to cross-validate the estimator least squares regression. And one small new import from ISLP, the ordinary least squares regression we saw in chapter 3 was actually from stats models, which is not part of scikit-learn. So there's a little wrapper here, so we can cross-validate the stats models using the scikit-learn sort of formalism.
And as in previous labs, we've put all the imports right at the beginning, so it's very clear what's needed to do the lab.
Yes, that's sort of best practices felt in Python because, well,
okay.
So we know what is in the namespace when we start. Okay, so let's run these cells because we'll have to run them to run the code. Okay, so we're going to use the function train test split that we saw in chapter 4 to split our, in this case, the auto data set where we try and predict miles per gallon as a function of different features of the car. We're going to split the data set of size 392, we're going to split into two equal size data sets of size 196. And we'll do as we did in chapter 4. We're going to fit the least squares regression on the training data set. And then we're going to evaluate the mean squared error on the validation or the test data set. So this HPMM, that's our model spec or model matrix constructor, and it will construct the design matrix for the validation. This is the response for the validation or test data. And we're just going to find the predicted values and compute the MSE. So our estimated SME is 23.62. So we might, this was just using horsepower as a linear term. We might want to use something like the train test split to pick an order of polynomial. Like in the classification chapter, we used it to compare different models, but here we have the model is the order of the polynomial. So we're going to make a little loop in order to compute the MSE for a few different orders of polynomial. So here's a little helper function to help us encapsulate what we did above for the train and test split that we'll use to evaluate in a for loop. This is the first example in the lab we've seen of a for loop. We're going to construct our model spec on different polynomials of different degrees of horsepower, and we're going to store the results in the MSE vector. Okay. So we see for the linear effect 23, and we see a pretty big improvement going to quadratic and less improvement going further. So there's really not much of a gain, it seems to be going from quadratic to cubic.
In fact, it looks like it's a loss.
Yes.
In this case.
Yes. Yeah. And of course, there's no guarantee that on the test data it would be an improvement, but on the training data, of course, we know it's an improvement.
So this is on the validation data.
Yes, this is, we've trained on the training data using the same split for every degree and then evaluated on the validation data. Okay. And of course, for different splits, we chose one split into 50-50. There's many different splits into 50-50. We might get slightly different answers. So we're going to change the random seed. Above the random seed was 0, I think. Doesn't really matter what it is. Here's a different one. And we'll rerun the same code. And we see we get qualitatively similar results, of course, but the numbers are different. The linear one has an MSE of 20.7 instead of 23.6 or so. Okay, so that variability we saw in test train split is related to the actual splitting into the two halves, and there's some randomness involved in that.
And also, Jonathan, we split our data set, which isn't that big to start with, into two pieces. And so now we've got half the data is used for training and half for testing. Doesn't seem a good use of the data, right? And so you're going to tell us about cross-validation, how you can do it more efficiently and get bigger training data sets in the process.
Yes, that's right. For every split into 50-50, the actual estimator has half the data set to work with. And cross-validation is a method. For instance, leave one out cross-validation. Every estimator there has 391 data points instead of 196. So the estimators are better, and it's a slightly different estimator because it's trained on more data. But it also reduces some of the variability you see in split to split in cross-validation, because it uses every data point gets treated as a test point. Okay, so as I mentioned above, scikit-learn has a very nice way to cross-validate many different estimators. That's this cross-validate function. Okay, so let's just look at our first example of cross-validation. We're going to cross-validate in the regression model with just a linear effect for horsepower. So this sklearn_sm is a wrapper that takes a method from a fitting method from stats models, in this case ordinary least squares, and a design or a model spec, and creates something that scikit-learn is familiar with, and that scikit-learn can use for cross-validation. So the main function in this chunk here is this cross-validate function here. So it takes, this is an estimator that scikit-learn is aware of. It takes a set of features and a response, and then an argument about how to do cross-validation here. And here I've given it the number of rows in auto.shape. So this is n-fold cross-validation, also called leave one out cross-validation.
Oh, so auto.shape 0 is the number of rows.
That's right, yes.
And so if CV equals n, it means you're going to have leave one out cross-validation.
That's right.
N-fold cross-validation. Yeah.
Yes, that's right. So this model, HP model, will be fit n times, each time with n-1 data points. Okay. So if
that's pretty quick.
Yes, computers are pretty fast these days. So if we wanted to change this to tenfold cross-validation, one of the nice things about sklearn is we just change the method of this argument we passed to cross-validate. So let's skip down to that. This one here is tenfold cross-validation. So we're going to, this object here, CV, I've called it, it's going to be k-fold with 10 splits. The shuffle equals true and random state equals 0. That's just to make sure that it's a random one. If without these, it just breaks it into 10, regularly spaced, but that's neither here nor there really. Okay, so so now when we pass this CV argument to cross-validate, it will only fit 10 models each time with a roughly 90% of 392, whatever that is, roughly 350 data points. And one of the other thing we've done here is we made a for loop to cross-validate for every different power, for up to fifth order powers of horsepower. What's happened is I've skipped ahead without running all the code necessary. So let me just run all the code up to here and run that again. Okay, so now we get, as a function of the degree, we have this cross-validation estimate. And note these are pretty similar to what we had for the test and train split, and the same pattern of no improvement going beyond quadratic for the degree of the polynomial. Okay, so you can also do test and train similarly with cross-validation using this thing called, instead of k-fold, this thing called shuffle split. But we'll leave that for you to do offline.